students, in the last class we discussed about the what is meant by logic family and what are the different types of the logic families. So majorly the logic families are divided into two types based upon the components used, that is BZT and FET. So the first of all the BZT logic family, so it can be again divided into two types, that is based upon saturation and non-saturation. So in the saturation logic families, we have to discuss about what is meant by RTL logic and what is meant by DTL and DCTL and TTL logics. So at the same time, coming for the next one, in the last class session, we discussed about what is meant by TTL logic. So TTL logic nothing but transistor logic. Here the transistors plays a major role for designing of any logic family. So transistor logic is mostly used in logic family. So in our day-to-day life, why? Because compared to the all saturated logic families, so this logic family is very much faster. So that's why TTL logic family is most advantage, nothing but mostly used logic family. So at the same time, coming for the non-saturated logic families. So in the non-saturated logic families, we have to discuss about, so it can be divided into two types, that is Schottky TTL and ECL. So at the same time, we have to discuss about the ECL logic family. So among these logic families, the ECL logic family is a peculiar thing, nothing but, so all the logic families are operated with a positive logic, except the ECL logic. So ECL logic nothing but emitter coupled logic. So the emitter coupled logic which is operated with a negative logic. So that is a very interesting thing about the ECL logic family. So why? Because here it as a designer point of view, so it can be designed with a negative logic and it has some advantages. So among all logic families, coming to the BZT logic family, the ECL logic family is very faster one. So due to this condition, the ECL logic family is mostly used at super fast computers, nothing but within seconds operations. So we have to use the ECL logic family. So we have to perform the operation with a very fastly manner. So then we go for the ECL logic family. So after that, the power supply, here the power supply is more stable. So coming for the ECL logic family, the supply is more stable. So at the same time, it has some disadvantages, that is power consumption is more. At the same time, somewhat it is difficult to design. Why? Because negative logic, that's why it is very difficult to design. And noise margin is also very high. So noise margin is reduced, not high. Why? Because noise margin nothing but we have to say that simply with extra noise which is added to that particular logic family which can't affect the circuit. So that thing is known as the noise margin. Here the noise margin is very less for the ECL logic family, and at the same time problem of cooling. So problem of cooling nothing but here the cooling simply indicates that, so that is easily heated. So that's why we have to cool that particular ECL logic family so many times. That is a problem of the ECL logic family. And there is another logic family, that is Schottky TTL logic family, comes under the non-saturated logic family. So what is the difference between TTL and Schottky TTL? So the only difference between these two things is, in the TTL logic family we have to go there, that is the logic family will be go to the saturation region. So that is we have three regions: active, saturation and cutoff region. In the TTL logic family we go for the saturation region level. That is the operation is performed in the saturation level only, saturation region only. But coming to the Schottky TTL, so we don't go to the saturation. So just in between these two, that is coming to the cutoff region and saturation region, there is another region, that is active region. So without going to the saturation region, we have to perform that particular logic. So for this condition, we add a barrier in between base and collector junctions. Simply the Schottky TTL will be like this. There is a barrier. Like this. So This is a Schottky TTL symbol, nothing but the designing. Simply the base, in the base and emitter collector terminals, there is adding of an extra diode, that is Schottky barrier, we have to know call it as. So this is so reduce the nothing but the speed of operation will be more. Why? Because so without going to the saturation region, we have to perform this operation. So that's why the speed of operation will be increased. At the same time, here, so the delay will be very less. So that's why, so coming to this, compared to the TTL logic family, this logic family is faster. So at the same time, the symbol of this particular TTL logic family, that is Schottky TTL logic family, will be like this. Just we add this thing. Just we have to add the diode. So then this becomes a Schottky TTL, and this is about the Schottky TTL logic family. So these are about the BJT logic families. That is what is meant by BJT logic family and what are the types of the BJT logic families we have to discuss. And next we move on to the FET logic family. So FET nothing but field effect transistor. Here we use the MOSFET. So that is metal oxide semiconductor field effect transistors are used. So the MOSFETs are again divided into three types, that is N-channel MOSFET, P-channel MOSFET and C-MOSFET. So for P-MOSFET, so what is meant by P-channel MOSFET? What is the symbol of P-channel MOSFET? Simply the symbol of P-channel MOSFET will be like this. So it can be represented with the dot. And the terminals will be gate, drain and source. And coming to the N-channel MOSFET, so this is P-channel MOSFET. And coming for the N-channel MOSFET, it will be like this. So for P-channel MOSFET, we have to give the 0 volts to this particular P-channel, so then it can be on. But coming for the N-channel MOSFET, so we have to give the 1 volt, then it can be on. So that is a 5 volt signal is applied to this particular one, then it can be operated. So that is about this CMOS logic family, that is MOS logic family. And PMOS can be also designed like this. So this terminal is known as gate, drain and source. So in place of bubble, we have to represent like this also, like this arrow mark. So this arrow mark indicates that P channel, and so this type of arrow mark in the reverse direction indicates the N channel MOSFET. So that is about the MOSFET. So the combination of these two things, the combination of P channel and N channel MOSFET forms the C MOSFET. Before going to the C MOSFET, we have to discuss so first we have to discuss C MOSFET, then we go for the N channel MOSFET inverter and N channel NAND gate and N channel NOR gate. At the same time, what is the CMOS NAND, CMOS NOR, and we have to discuss that things. So that is the CMOS so here we use the MOS transistors, and PMOS and NMOS are the basic building blocks of this particular thing. So any CMOS logic family is designed with the combination of PMOS and NMOS. So here we use the PMOS and NMOS. So both we have to use. At the same time, here the logic 0 is represented with the 0 to 1.5 volts and logic 1 is represented with the 3.5 volts to 5 volts. And coming to the advantage of this CMOS logic family, faster compared to the bipolar logic. So compared to the BJT logic, here this logic family 1 will be very faster. So at the same time, so the another important thing is it is simple to fabricate. So fabrication is also very simple and less power. It consumes less power. So these are the advantage of this thing. Simply we have to say that. So faster operation it can be performed compared with the BJT logic family, and power consumption will be less and easy to fabricate, and compared to the previous logic family, that is BJT logic family, here the noise margin is very less. Nothing better noise margin it can be provided. So and here, so another important and particular thing about this one is the power consumption, that is the power dissipation is low. So the dissipation of this power will be very less, and at the same time the CMOS logic family is faster than the BJT logic family, and the power consumption will be very less due to this reason, that is a very less power consumption. So that's why it is used in the handheld devices. For designing of handheld devices, we go for the CMOS logic families like smartphones, watches, cameras. So these are the examples of these CMOS logic families where we use this CMOS logic family. Simply we have to say that in that particular examples are nothing but in that particular conditions we use this CMOS logic family. Why? Because here the power consumption is very less. So that's why we go for this CMOS logic family. So that is about the CMOS logic family, and let us discuss about the before discussing about the CMOS inverter, we have to discuss about the NMOS. So what is the NMOS inverter? Next we go for the NMOS NAND gate and NMOS NOR gate. First one is NMOS inverter. So what is meant by NMOS? N-channel MOSFET. So where it can be on, simply we have to say that for 5 volt signal only it can be operated. So when we apply 5 volt signal to this particular MOSFET, then only it can be operated. So simply this NMOS inverter can be like this. Here the output is taken in between these two things, and here we apply the VCC, and one of the terminal of this thing, that is these 5 volts is applied to this first NMOS. So this is a very important thing. So when this transistor is on, during that time only, so the VCC signal is given to the output. So that's why obviously this signal will be nothing but obviously this condition will be on only. So that is this is the NMOS inverter. So when we apply, this is taken as A. When we apply A is equal to 0. So that is A is equal to 0. During that time, this MOSFET can be acts as open circuit. Nothing but it is in off condition. So that is this transistor is always in on condition. That's why this 5 volt signal is reached here. So when 0 volt signal is 0 is applied to here, so then the transistor of this one, this will be off condition. That's why this VCC signal will be produced at the output side. Next, when A is equal to 1, so that is A nothing but 1, nothing but we have to take it as logic 1. Logic 1 nothing but 5 volt signal. When we apply a 5 volt signals to this N-channel MOSFET, obviously the N-channel MOSFET will be on condition. So that's why, so both the transistors will be on condition. This VCC will be reached at the ground side. That's why the output will be 0. So that is simply we have to say that when a 0 volt signal is applied to this, the output will be 1. When 1 volt logic 1 is applied to this, then the output will be 0. So simply this circuit can be acts as an inverter. So next we have to discuss about the NMOS NAND gate. So that is NMOS NAND gate. What is meant by NAND gate? It is a reverse to the AND gate operation. So simply we have to say that that is here very important thing. So in the NAND gate design, the NMOS will be connected in series, and NOR gate, the NMOS will be connected in the parallel. So simply the first thing will be as usual common. So that is this VCC, this one is connected to the VCC, and next one they are connected in the series manner. Here it can be represented with A and B, and this one will be output. So that is A, B and output. When the signal will be 0, 0. So that is here the 0 and here also 0. When both the signals will be applied to the 0, 0, then so this transistor is in always on condition. Why? Because here a 5 volt signal is applied to this, and this one will be 0, 0. Both are in off condition. That's why this is replaced with the short switch. Simply the output will be a VCC. And 0, 1. So when we apply 0, 1, so this transistor is in off condition and this transistor is in on condition. So any one of the transistor is in off condition, obviously there is no path of VCC signal to reach at the ground. So that's why the output will be VCC, simply a logic 1, here also a logic 1 and 1, 0. This is VCC and logic 1 and final one, that is 1, 1. So that is A and B both are 1, 1 condition. So simply we have to say that both the transistors, that is MOSFETs will be on condition. So that is we have to say that this VCC signal will be reached at the ground. So that's why the output will be 0. So that is logic 0. So this is NMOS NAND gate. So next we have to discuss about the NMOS NOR gate. Simply the NOR gate is so just here we have to connect that NMOS devices in series. Here we have to connect the NMOS devices in parallel. So that is the only thing. Ground in A and B. Here we have to connect A and B. When here the output is taken here, when we apply the 0, 0, so then both the transistors are in off condition. So there is no path to VCC reached at the ground. That's why the output will be VCC. So that's why the output will be logic 1. So when any one of the transistor is in on condition. So when we apply 0, 1 or 1, 0 or 1, 1, any of the condition, one of the transistor is simply on condition. So there is a path of VCC signal to reach at the ground. That's why the output will be 0. So this is an operation of NOR gate. Simply, so any NMOS or CMOS or PMOS are designed for the universal logic gates. By using this, we have to design the universal logic gates most of the cases. And with the universal logic gate with the inverter connection forms a normal AND gate or OR gate. So simply, so we have to say that most of the cases we use that conditions for the universal logic gates. And next, so same like that we have to design the CMOS inverter. So the CMOS inverter is a combination of P channel MOSFET and N channel MOSFET. First we have to take the P channel MOSFET, that is and N channel MOSFET, which is connected to the ground, and both will be connected with each other with the input A, and here we have to connect the VCC. First I am giving a input signal A, so A is equal to 0. What happens? Output is taken here. When A is equal to 0, then this transistor is in off condition. Sorry, when the 0 input is given to the P channel, then transistor is on condition, N channel is going to off condition. So that is when input A is 0 is given to this particular one. So then PMOS is on and NMOS is off. So simply we have to say that when PMOS is in on condition, it can be replaced with a short switch. So that's why the VCC signal will be reached at the output side. Simply the output we have to represent with the output is equal to VCC, which is represent with the logic 1. Next, A is equal to 1. I have to represent with A is equal to 1 condition. So then what happens? This PMOS is off condition and NMOS is in on condition. So here this MOSFET is in off condition. Simply there is no path of VCC signal to reach at the output. So that's why the output will be 0. That is 0. Logic 0. So this is about a CMOS inverter. As like that we have to indicate that N channel, so NAND gate, that is a CMOS NAND gate and CMOS NOR gate. So as the first thing in the CMOS NAND gate, so very important thing in the CMOS NAND gate, any NAND connection will be connected in the series manner for NMOS and it is reverse for the PMOS. So simply we have to say that A into B bar, like that we have to represent AB bar, which can be connected series in NMOS and parallel in PMOS. And A plus B bar, that is NOR connection, parallel in NMOS and series in PMOS. So any of the circuit, we have to follow these conditions. So any NAND connection we have to represent, that can be series in NMOS and it can be reverse in the PMOS, that is parallel in PMOS. And coming for the NOR gate, so in the NOR gate the NMOS will be series and parallel, so the PMOS is in series and parallel for the NMOS, like that. So for example, first I have to represent that cmos NAND gate. How to represent this cmos NAND gate? So it can be like this. So first in parallel for PMOS, like that it can be represent. We have to represent this VCC. After that they connected in series with ground. Both will be connected to the A, and here it will be connected to the B, and the output is taken here. So then we have to give an input, that is A, B, and here I am representing this one will be Q1, Q2, Q3 and Q4. Q1, Q2, Q3, Q4 output. When both the inputs will be 0, 0, what happens? When both the inputs will be 0, 0, Q1, Q2 both are on condition and Q3, Q4 will be off condition. Why? Because so we have to give the 0, logic 0, nothing but 0 volts. So if a 0 volts, the PMOS will be on and NMOS will be off. So that's why the Q1 is on and Q2 is on and Q3 is off condition and Q4 is off condition. During this time the output is simply we have to represent both are in on condition. So that's why there is a chance of VCC signal to produce at the output side. The output will be VCC. So next we have to give the 0, 1 signal. So that is 0, 1 signal we have to apply here. So then simply we have to say that the transistor Q1. So that is Q1 nothing but Q1 is in on condition and Q2 will be off condition. That is Q1 is on and Q2 will be off condition. Why? Because we apply 1 volt signal to the B. So then Q2 is in off condition. And at the same time, what is the condition of Q3? Q3 is off. Why? Because we apply 0 volts to the Q3 and 1 volts to the Q4. That's why Q4 is in on condition. So any one of the transistor is on condition. That is either Q1 or Q2. Any one of the transistor is on condition. Then the VCC signal will be reached at the output side. That's why the output will be VCC is simply logic 1. Here also logic 1. So then we apply a 1 0 signal. A 1 0 signal is applied to here. Simply it is reversed to that. That is off. The transistor Q1 is in off condition. And what is the condition of transistor Q2? Q2 is in on condition. Q3 is in on condition and Q4 is off condition. Simply the output will be VCC, which can be represented with the logic 1. So next we have to give the 1 1 signal. So during that time, so when we apply 1 1 signal to this particular one, then transistor Q1 and Q2 both are off condition. Why? Because so it is an NMOS. So when we apply 0 volts to this particular one, during that time only it produces the, so that is it is on condition. So simply we have to say that both are off condition and N channels are on condition. So in this time there is no VCC signal to reach at the output side. So that's why the output will be 0. So simply this circuit can be acts as a NAND gate. That is 2 input NAND gate circuit. So and As like that, we have to represent the NOR gate circuit also. Simply the NOR gate circuit is reversed to this particular one. So the P channel MOSFETs are connected in series and N channel MOSFETs are connected in parallel to this. So let us discuss about the CMOS NOR gate circuit. So what is that circuit? Let us discuss about this. So that is reverse to this N channel MOSFET, that is reverse to the CMOS. Simply the PMOS will be reversed. In the previous we have to connect in the PMOS in a parallel manner. Here we have to connect PMOS in series manner. That is this PMOS is connected in series like this. And NMOS will be connected parallelly like this. Both the A inputs will be connected with each other and the B inputs will be connected with each other like this. Here it can be represented with Q1, Q2, Q3 and Q4. So this one is A and B. Sorry, this one is A and B. When both the inputs will be 0, 0. So during that time when both the inputs will be 0, 0, here the output is taken here. Simply we have to say that we apply 0 volts to this Q1, Q2 at the same time Q3 and Q4. In this particular time, so Q1 is on and Q2 is on, Q3 is off and Q4 is off. Simply both transistors is on condition. In a series connection, when these two transistors is in on condition, signal will be reached at the output side. Simply here when we apply 0 volt signal to these both transistors, then only these two transistors is on condition. Simply the output will be VCC. So that is logic 1. Next we apply 0, 1. So during that time, so the Q1 is, what is the condition of Q1? Q1 is on and Q2 is off and Q3 is off and Q4 is off. So there is only one transistor is on condition. Simply another transistor blocks this VCC. That's why the output will be 0. The output will be logic 0. So in the next conditions also the output will be simply logic 0. So this is about the operation of the NOR gate in the CMOS design. So this is about the CMOS logic family. So among all logic families, CMOS logic family is used. Why? Because the power consumption will be very less. So that's why it is used in the handheld devices like smartphones, smartwatches and our day-to-day calculators like this. So this can be mostly used. So let us discuss about the comparison of the all logic families. So what is the comparison of all logic families? Simply, what are the major things we have to compare for the logic families? So that is, the first one is basic gate. So the RTL logic, first we have to discuss about the BJT logic. In the BJT logic, the RTL logic is the first one. So in the RTL logic, the basic gate is a NOR gate. So this particular logic is used for designing of the NOR gate only. Next, I2L logic, that is NOR gate, and DTL is NAND, and DTL, HTL and TTL, these three are used for the NAND gate designing only. And the next one is the ECL logic, that is very interesting logic. It is used for both OR and NOR gate design. By using this, we have to design both OR and NOR gate, and most logics are used for the NAND and NOR gate design. And that is about the basic gates. So what are the basic gates for designing of this particular logic family? And next one is fan out. What is meant by fan out? Number of outputs which can drive the circuit, or number of outputs a gate can drive. So RTL logic will be 5 and DTL is 8 and HTL is 10 and TTL is 10 to 20. Among these all logics, the CMOS logic family fan out will be So it is up to 20 to 50. So more fan out will be done with the CMOS logic family. And the next one is power dissipation, that is it will be less in the CMOS logic family. So that is very advantage thing compared with the all logic families. So and the next one is propagation delay. So what is meant by propagation delay? The time taken a signal, that is a time taking a input waveform to reach at the output side. So this is known as a propagation delay. Simply, so the propagation delay will be less in the TTL logic, sorry, ECL logic family. That is within seconds only we get the input signal at the output side. So that's why this ECL logic family is used at the super fast computers. And the next one is clock rate. So the clock rate is 2 for the MOS transistors. At the same time, final one is available functions. So that is most of the cases like LSI or MSI, anything like this. So most of the cases the ECL logic family is very high and TTL is also high. Nothing but. So most of the cases we use a TTL logic family in our day-to-day lives, and the ECL logic is also used, but that is very different thing. Why? Because the cost is very high, that's why it is used in the super fast computers, and CMOS logic family are also mostly used in our day-to-day. So this is about the logic families in the 6th unit. In the next class, we discuss about what is meant by sampling gate and what are the types of the sampling gates.